In this lecture we are going to compare half bridge circuit with the full bridge circuit. The circuit diagrams for both of these are shown in front of you, and the waveforms for the resistive load are also shown. So these are the output voltage waveforms, and we already know that in the case of the full bridge inverter the output is double as compared to the input. So we are now going to calculate some parameters, and we will compare these two inverters in terms of those parameters. So first of all, let's look at the output voltage in terms of the Fourier series. This can be written like this, that is equal to 2 Vs by n pi into sine of n omega t. Why 2 Vs? Because our output voltage varies from minus Vs by 2 to plus Vs by 2 in the case of the half bridge inverter. However, in the case of full bridge inverter, our output voltage varies from minus Vs to plus Vs, and we have double voltage in the full bridge inverter. So its Fourier series representation will be like this. For all odd harmonics, 4 Vs by n pi into sine of n omega t. Okay, now from these expressions we can calculate the fundamental component V01, representing the fundamental component of the output voltage, that will be equal to 2 Vs by pi. That's the peak value of the fundamental component. And if we calculate the RMS value of the fundamental component, so that will be equal to 2 Vs by under root 2 pi. Similarly, for the full bridge inverter, output peak value will be equal to 4 Vs by pi, and the output RMS value of the fundamental component will be 4 Vs by under root 2 pi. So now if we simplify this one, V01 can be written as 0.45 into Vs, where this is the RMS value. And similarly, for the full bridge inverter, the RMS value of the fundamental component can be written as 0.9 into Vs. Okay, now if we calculate the output RMS of these two inverter circuits, so that can be calculated with the help of this expression, that for output voltage we will have to take the area under the curve, and for that we can write down this expression. This is 2 by time period integration from 0 to half of the time period of the function, and the function is Vs by 2 whole square, and integrating it with respect to the time. So if we simplify this one, this will be equal to Vs by 2. So your output RMS value is simply equal to Vs by 2, that's the peak value of your square waveform. So in this particular case, we will be comparing these two inverters by considering the same source voltage and the load resistance. So if we calculate the output RMS value, that will be equal to 24 volt in the case of half bridge inverter, and in the case of the full bridge inverter, if we apply the same expression, so V0 will be equal to under root of 2 by time period integration from 0 to T0 by 2 of Vs square with respect to time. Okay, so simplifying this one, we will get Vs. So output voltage in the case of full bridge inverter is equal to the peak value of your square waveform, that is 48 volt. So output voltage is double in the case of the full bridge inverter. Okay, now let's calculate the power that is delivered by these inverters. So the output power will be given as V0 square by R. So our voltage is 24 volt, and divided by 2.4 ohm resistance, so you will be getting 240 watt. And same thing if we calculate for the full bridge inverter, so P naught will be equal to V naught square by R, so this will be 48 square by 2.4 ohm, so this will be equal to 960 watt. So from here you can see that for the same supply voltage and for the same value of the load, we are going to get significantly higher power output from the full bridge inverter. Now let's compare the peak transistor current. So peak transistor current, so that can be calculated in the case of half bridge inverter by dividing the peak voltage that can appear across your load, so that is 24 volt, so dividing it by 2.4 ohm resistance, so there will be the 10 ampere current through each transistor. And if we calculate it for the full bridge, so peak transistor current in full bridge will be higher because it has 48 volt at the output and resistance is 2.4 ohm. So 20 ampere will be the peak current in the case of the full bridge inverter. So the current rating of the switches will be double as compared to the current rating of your half bridge inverter, but at double peak rating we will be getting significantly high power at the output. Okay, now let's calculate the average current of each transistor. So average current of each transistor, so let's denote it with IQ. So total current is 10 ampere, but there are two switches. If we want to find out the average, so the half of the current will be going through one switch and the half of the current will be going through the other switch. So just 0.5 into 10 ampere, that is the 5 ampere is the average current of each switch. Similarly, if we calculate it for the full bridge inverter, so 0.5 into 20 ampere, so 10 ampere will be the average current of each switch. Okay, now let's look at the peak reverse blocking voltage in each case. So peak reverse blocking voltage of the switch, we just write down or represent it with VBR. So what that will be equal to, if I go and look at the circuit, if you consider this switch S1, how much reverse voltage it will have to withstand. So when your switch S2 is in the on state, so the voltage across your switch S1 will be Vs by 2, and similarly when S1 is in the on state, S2 is off, so voltage across that one will be S2 Vs by 2. But in the worst case, this full supply voltage can appear across the switch when it is in the off state. They will have to block this supply voltage. So VBR rating for the switches is equal to 48 volt, and same is the case of your full bridge inverter, that each switch at the maximum can have 48 volt, and that switch will have to block that voltage. So VBR for full bridge inverter and for half bridge inverter is same, 48 volt. Okay, now let's compare the harmonic voltage. Okay, so harmonic voltage can be calculated by summing up the RMS values or the peak values of the individual harmonics. So we represented VH and we calculate it with the help of this expression, that summing up all the harmonics, and there will be odd harmonics in the square waveform. So excluding the fundamental component is not considered, so that component of your output voltage will be considered. So we can represent harmonic voltage with this expression, and this can be written like that: the total output voltage, from that if we subtract the fundamental component of the voltage, you will get the harmonic contribution. So if we simplify it, using the previous expression, we know that V01, the fundamental RMS voltage, that is for the half bridge, is given as 0.45 Vs. So using this I can write it like that V0 is equal to 0.5 into Vs, so 0.5 into Vs square minus fundamental component is 0.45 Vs, so 0.45 Vs square. So if I simplify this one, I will get 0.2176 into Vs. So harmonic voltage will be given by this expression. Similarly, if we calculate the harmonic voltage for the full bridge inverter, we know that V01 is 0.9 into Vs, and V output is equal to simply Vs, the total RMS voltage. So harmonic voltage will be equal to V0 square minus V01 square, so that will be equal to 0.4359 into Vs. So harmonic voltage in the case of full bridge inverter is higher as compared to your half bridge inverter for the same supply and the load condition. Okay, now let's calculate the THD, total harmonic distortion, in the voltage. So THD, as we know, is given by the comparison of the harmonic voltage with the fundamental component of the voltage at the output. So you can consider the peak value of the harmonic, then you will have to consider the peak value of the fundamental, or you can consider the RMS values. Both should be of same nature when you are using those ones. So as we have calculated the RMS values above, so if I calculate the THD, so I can do it like that: 0.2176 Vs, that's harmonic voltage, divided by the fundamental component. Fundamental component is 0.5 into Vs, so the THD for this particular case comes out to be 0.4835. It means 40.35%. Similarly, if we calculate the THD for the full bridge inverter, the expression is same for harmonic voltage compared with the fundamental component, so that is equal to 0.4359 into Vs divided by the fundamental component, that is 0.9 into Vs. So if you calculate that one, you will see that their THDs are nearly same: 0.4843, that is 48.43%. So THD in the voltage, either it's a half bridge inverter or the full bridge inverter, both are the nearly same. Okay, now let's calculate the distortion factor. But to calculate the distortion factor, we will have to first of all evaluate this expression. So let me call that K is equal to summation of all the harmonic up to infinite into V n divided by n square and the square of that one. So this can be written as V third harmonic component ka square plus fifth harmonic component contribution, then seventh harmonic component, and so on up to all the harmonics. So if we simplify this one, this K will be equal to 0.024 into Vs, and if we calculate the same thing for the full bridge inverter, so that's the K. So the K is the summation of the all harmonic contributions subjected to the second order attenuation. So this comes out to be 0.048 NVS. For detailed discussion about this K and the distortion factor, please refer to our previous video. In one of previous video I have explained this one in detail. Okay, now let's calculate the distortion factor. Distortion factor is given is defined as K by V01. So we have calculated K, just plug in the values over here. So our distortion factor will be 0.0533, or if we write in terms of percentage, distortion factor is 5.33%. And if we calculate it for the full bridge, the distortion factor will be same. So both of them have the same distortion factor. Distortion factor is basically the factor which gives us an information of the amount of the harmonic distortion that remains in particular waveform after the harmonics of that waveform have been subjected to the second order attenuation, right? So that's why your terms are divided by n square. And distortion factor is a measure of effectiveness in reducing unwanted harmonics without having to specify the values of a second order load filter, right? So now let's look at the LOH, lowest order harmonic, and what is that one? We have already discussed in the previous video. The LOH is that harmonic component whose frequency is closest to the fundamental one and its amplitude is greater than or equal to 3% of your fundamental component. So now if we calculate the LOH, Fourier series expression for the waveform is known to us. So in both cases, if we calculate the magnitude of the third harmonic, so that will be V01 by 3, right? So if we look at in terms of percentage, this harmonic factor for the third harmonic, that will be equal to V03 divided by V01, so that comes out to be 33.33%. So it fulfills the definition of the LOH, lowest order harmonic. So our lowest order harmonic is the third harmonic, right? So similarly, in the case of the full bridge inverter, our LOH is also the third harmonic, right? And okay, so now if we calculate the distortion factor for the particular harmonic, let's suppose the third harmonic, that is the LOH. So DF3, distortion factor because of the third harmonic, so that will be given as V03 divided by 3 square into 1 by V01. Okay, so just we know that V03 is equal to V01 by 3, and how we know about this one, because V0 is equal to 2 Vs by n pi summation over all harmonics into sine of n omega t. So you from here you can see for if we calculate the magnitude of the harmonics, so if you do it for the third harmonic, so that will be 1 by third of your fundamental component before from this expression. Okay, so just using this data and placing it over here, you will get it equal to 1 by 27. That means the distortion factor because of the third harmonic when subjected to the second order attenuation will be 3.704%, and same will be the case for the full bridge inverter. If you calculate the distortion factor of the third harmonic for the full bridge, so that will be given by this expression, and after calculation you will get the same value. So both of these inverters give you the same distortion factor. They have nearly the same THD. They have better improvement. They have the difference in the terms of the output voltage they provide to the load. Okay. So that's all from this video. Thank you.